Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last couple of classes, we started discussing the finite volume approach, which is very popular in basically in commercial software or open source software. Okay, and we looked at how we use the integral form of the governing equations in the finite volume approach compared to the basically differential form or the strong form in the finite differential approach. We saw that as soon as we use the integral form, basically we can use any kind of elements that we want. So, in 3D it can be polyhedral like hexahedral, tetrahedral, prisms, pyramids, all these kind of elements can be supported. In 2D it will be maybe the polygon, triangle, then quadrilateral, all those kind of elements are supported, right. So, this gives us the flexibility that we can use the finite volume approach for more complicated domain. Okay. In fact, this is the approach that is used most commonly when the simulation domain is quite complicated or the geometry is quite complicated. Okay. So, let us continue the discussion. Okay. So, what we saw that when you use the integral form of equation, we basically get our state update formula, which is like an ODE. Okay, where the right hand side you basically will be calculating the fluxes, and the left hand side you can use your favorite time scheme here. Okay. So, if you have let us say domain like this, okay, and this I am calling as capital J as the interface, okay, and this is my I, okay, and if you want to calculate the variation in I, then all you need to do is basically calculate the fluxes at all these three interfaces. Okay. So, you have j equal to 1, j equal to 2 and j equal to 3, okay, and multiply with the area. So, this will be your delta S j. Okay. In the 3D it will become the cell volume. So, this is in fact called the cell volume. In 1D it will be just the delta x, right. So, if it is just 1D, so this is a general formula. We had used the Gauss divergence theorem to derive this formulation. Okay. So, if it is 1D, so this is my I, and this is my I plus 1, and this is my I minus 1. Okay. So, this is my interface here, you can call it J, or it may be you can call it I plus half, and this is another interface. So, in 1D each cell will have two interfaces, and in fact, this is my cell, right. So, then J equal to I minus half, okay, and if you use this formula, okay. So, if you look at this interface, your velocity normal is in this direction. So, it is nothing but just I, okay. Here this I is basically I j k, because the coordinate axis, okay. This represents x direction. In fact, I should write it 1 0 0 maybe, okay, to avoid this nomenclature. So, n is nothing but 1 0 0, okay. That means unit normal in the x direction, and because the 1D flow there is nothing in the y and z direction, okay. And in this side if you do n is equal to, this is minus 1 0 0, right, because the area normals are always perpendicular to the interface. So, if you use this formulation, this will become dui by dt, where ui is the value at the cell center, okay. Sometimes it is also called cell centroid, okay, minus 1 by omega I sigma f perpendicular j delta s j. So, what is the delta s here? Okay. So, this would because it is a 1D flow. So, this will just become 1. So, this is minus 1 by omega I and f perpendicular j. So, I am looking for this face now, face on the right hand side, okay. So, that will become you can write it as f I plus half, okay, and delta j. So, area is because it is just 1D flow, right. In 2D how do you get this? So, this distance is the area, right. In 3D it will be the face. So, it may be a triangular face, then the area of the triangle, or if it is a quadrilateral face, then area of the quadrilateral. In 1D it just it will be 1, right. This is f j plus half into 1 minus plus, because this is a plus sign here, sigma sign, f I plus I minus half and then minus 1, right. So, we are basically looping over all the faces. So, f I minus half, we are looking at this face now, this one. Okay. So, this is f I minus half and the direction is minus 1. So, area normal is minus 1. So, and this omega I is nothing but the distance from here to here, which is my delta xi. This is called the cell volume for the general terminology. So, this is minus 1 by delta xi, f I plus half minus f I minus half, right. And here is like an ODE and you can use your favorite scheme. Okay. So, if you are using it the let us say Euler forward. So, u I n plus 1 minus u I n by delta t, right, and solve it and you will get it. Okay. And then we discuss that this formulation basically preserves conservation. Okay. So, the conservation is in the local conservation as well as global conservation. That means that if you look at just this cell, okay, that I have made around I, okay, here also if you calculate the du by dt, is the whatever change is happening with time is due to the fluxes which are going out minus fluxes that are coming in, right. And similarly, if you take the global system, that means you are considering I equal to 1 to all the way to n. Okay. In that cases also the intermediate values, which is like let us say f 3 by 2, f 5 by 2, all of those all the way to f n minus 1 by 2 will get cancelled out. Okay. And you will get only the last two interfaces. Okay. So, the boundaries is what you will get. So, if you have a boundary here, if a boundary here, okay. So, this is f minus half and this is f n plus half, right. So, the overall difference in the flow variable, which is given by u here, is basically the change which is happening at the boundaries. Okay. So, this is what we mean when we say the global conservation. Same thing you can see in 2D also. So, in triangle also basically because we are using this formulation. Okay. So, we are making sure that in each cell the values are conserved. Okay. And globally also, if you consider all the cells together, then also values are conserved. So, it allows you the both local conservation and the global conservation. Okay. Now, the challenge that we had was that how to calculate this f I plus half and f I minus half at the interface, right. And what we said is that in the cell we assume a linear variation. Okay. So, then if this is the cell and things are changing linearly here. So, you can, if this is my u bar I and I want to calculate what is u bar I plus half, okay, maybe in that direction. Okay. U bar j you can call it there 2D. Okay. So, if you know the cell gradient here from the linear variation, you can get the cell variation here du I, okay, by dx and du I not the bar, okay, only the variation of u. Okay. U I bar is the cell average value. Okay. So, this is du I by del y, and then if you know the variation, you can basically calculate the gradients at the faces. Okay. And from that gradient you can calculate the fluxes, right. In 1D we saw that it is very trivial. Okay. You can just take the value, maybe take a upwinding scheme, okay, and this is I and this is let us say I plus half and this is j I plus 1 and this is I minus 1. So, you can probably consider I and I minus 1, get the gradient at du I, okay, and based on that you can basically calculate the values at the I plus half and I minus half. Okay. So, this is what we saw in 1D. In 2D it becomes little complicated, and we said that we will be using green Gauss and least square kind of approaches, but I did not elaborate on that. I thought that maybe you could basically read it at your home, but maybe it is important to discuss little bit about that, okay, because it is not that trivial. Okay, so I will be discussing the green Gauss as well as least squares approach in today's class. Okay. Before going there, so here we are considering only the everything that we have considered. The F is basically the convection term, okay, but you will also have the viscous term here. Okay, so if you include the viscous term, okay, things become little bit more complicated, because you can put all these things on the left. So this is my F inviscid and F viscous. Okay. So what you see that if you put all of this together, so if you have du by dt plus del dot F minus nu del u, okay, d omega, and then you can use this green Gauss the entire thing, okay, and you will be basically calculating du by dt will be equal to minus sigma F minus nu del u, okay, dot n j delta S c, right. Basically, we will be multiplying F normal. So, for that, for this F calculation, we needed the values at the cell interfaces. You needed what is the value of u at interfaces. So, basically u f, right, at all the faces. So, if this is my grid. So, I wanted this. So, this is f equal to 1, 2, 3. So, we wanted the value at interface here. But you can see that if you are using the considering the viscous flow, then you need to have the viscous gradient also, I mean the velocity gradient also, in fact the temperature gradient also at the cell face. Okay. So, not only we need u f, but we also need let us say del u by del x at f, del u by del y at f, right. So, we require both the values as well as its gradient on the interface. Okay. Always remember that our solution variables is stored at cell centers, or okay, or cell centroids. Okay, this is my I, and in the green Gauss approach or the least square approach, you typically get the cell gradient at I, and so that you can use the variation from I, the gradients from I to get the values at the faces, right. But now we also need the gradients at the interfaces. Okay, so how do you do that? So let us look at these things little bit more detail. Okay. Yeah, so this is what I have said, that you need the velocity gradients also. Okay. So let us go one by one. Okay. So we have two approaches, one we call as the least square formulation, least squares reconstruction. So this basically this approach or this path is called the reconstruction. That means how the flow variable is reconstructed within the cell. Okay, that is what we want to find out. If you know how the flow variable is varying inside the cell, then we can calculate the gradient, right. And then we also have this green Gauss approach. These are the two most popular approach. Okay, and you can see whether in open form or whether in fluent, you will have both these approaches. In fact, in green Gauss, you would see there are two approaches. One is cell based and other is node based. Okay, and this is there in both fluent as well as open form. In most of the softwares that you use, will have options for you to choose among these three. There is another approach called pseudo Laplacian, but that will not be discussing today. Okay. Okay. So, how do we go about this least square construction? So, first let us discuss least square. The least square, as we know, I mean it is a very general terminology, where if you have a system which is over determined, that means that let us say you have number of variables that you want to solve is 3, and number of equations that you have is let us say 10, okay, or let us say 5. So, then how do we get the values, the 3 values that gives you the least error, okay, while trying to satisfy these 10 equations. That approach is called the least squares approach. So, basically you take all the 10 equations, calculate the error, okay, and then try take the square of the error, and then you try to basically minimize the error, okay, with respect to your independent variable, dependent variable, and you basically calculate the values that you want to solve, okay. So if we have, let us say this is my cell, this is I, okay, and I have another cell which is neighboring cell which is J, right. So these are two cells that we have, okay. So what we can do, we can write, let us say that I know the value at u I and u j, and my target is to find what is the slope, basically what is del u I, okay, that means del u I by del x and del u I by del y, okay. This is my global coordinate system, this is my x, this is my y, right. So you can define let us say here the gradient u j e, okay, u j e here calculating from I. So that will become u I plus you know the, so this is my x and this is my y, right. So you take the gradient with respect to x, so this is del u by del x at I x j minus x I, okay, and plus del u by del y I y j minus I y a. Very simple, basically we use the Taylor series. So from I we are getting the value at j, okay. So this is the estimated quantity, you can estimate it with respect to many different cells. So this cell will have many neighbors, right. There is one neighbor here also, there is one neighbor here also. So this is one j, maybe you have k, maybe you have l, okay. So similarly you can write u j k, okay. So you can write here u j e, okay, or maybe u k e equal to u I plus del u by del x I x k minus x I plus del u by del y I y k minus y I, okay. Similarly you can write u k l, okay, u l estimated, okay, e is for an estimation, estimated value, that is u I plus del u by del x I x l minus x I plus del u by del y I y l minus y I, right. Now you need only two things here, okay, del u by del x at I and del u by del y at I, okay. These are the only things that you want. So you have two variables, and now in this you can see that you have at least three equations, okay, by considering the cell neighbors, okay. If you want, you can also consider the node neighbors, right. So for example, your node may be connecting to some more here, okay, similarly here also. So these are your node neighbors, okay, all the nodes consisting of this, okay, these are your node neighbors, okay. So these will also have the cell centroid, okay, and you can consider that. So in that case, let us say you are considering the node neighbors, then you will have 1, 2, 3, 4, 5, 6, 7 equations, right, in this particular case, right. So you have only two unknown variables, but you have many equations, right. These are the estimated quantities. So what we will do, you actually know the value at u j, right, do not you. So you know the value of u j, you know the value of u k, and you know the value of u l, right. These are the values which are stored at the cell centers, right. So what you can do, you can calculate the error, right. So your actual u j that you know minus u j estimated, right. So if you do that, so you will have this u j minus u I del u by del x I j minus x I and del u by del y I y j minus y I, right. So you can write it in terms of delta u j like this, right. So what you can do, so this j would vary in if you are considering the cell neighbors, okay, and the example that I saw shown earlier, okay, then j will vary from 1 to 3. So what you can do, you can take the square of j, okay. So because we are trying to basically minimize the error, of the Ej square. So, take the square of those values. Okay. And now, what are your target? Basically, you want to get del u by del x I and del u by del y I, right. So, differentiate this equation 2 with respect to these two variables, and as soon as you differentiate it. So, once you basically take the summation of all these things, okay, and then differentiate it. So, when you do this del u by del x I, when you try to differentiate with respect to that, you will get delta x j, and when you try to differentiate with respect to del u by del y I, you will get delta y j multiply by your E j. So, you will get these two equations, E j delta x j and E j delta y j, right. Now, you can expand it and write it. So, the first equation, this is E j delta x j and this is E j delta y j, right, sigma, right. So, now this is your equations that we have. Now, we can solve it. So, you have two equations and two unknowns, this is 1 and 2, right. So, we have two equations and two unknowns. So, you can solve with respect to this, solve for this delta u x by delta by delta x I and delta u x by delta y I, and once you solve it, you will get the gradients at the cell center. Basically, you will get del u by del x I and del u by del y I. Okay. So, what we did exactly in this, that for a given cell we considered its neighbor, okay, and we estimated what would be the gradient from this cell center to the its neighbors, okay, calculated the error and found out that what should be the gradient with respect to x and y, so that the estimated value is as close to the actual value as in the neighboring cells, right. In the 3D you will have 3 gradients, okay, partial to the partial x, partial to the partial y, partial to the partial z, right, but you will have more number of neighbors also, right. Consider a 3D element, right. Let us say if you consider a pyramid, right, so you will have 4 faces, right. So, you have at least 4 faces there. So, if you let us say consider a prism, okay, then you will have 5 faces, right, triangular prism. Similarly, you can have the hexahedral and polyhedral. So, you will have more number of neighbors, and on all those neighbors you can calculate this delta x by delta, I mean basically calculate all 3 gradients at each cell center, and then you can proceed it for all the cells that you have, right. And as I told you, you have 2 choices of neighbors, either you can share take the vertex sharing neighbors or you can take the face sharing neighbors. Okay. So, I think this is wrongly written. Okay. So, this is your face sharing neighbors. So, this is my grade that you want to calculate. Okay. So, these are the cells which are basically sharing the face. Okay. And similarly, you can basically look for the vertex sharing neighbors also, as I was giving an example, that if you have cell like this, you can see what are the cells which are basically connected to your vertex. Okay. And there can be many, normally the number of vertex sharing neighbors are much higher than the number of face sharing neighbors. Okay. So, that basically gives you a better approximation, but it is more expensive also. If you go for the vertex sharing neighbors, it is more expensive, but both of these works. Okay. So, this is how you get your gradients at the cell center using the least square. Okay. Now, let us go to the green Gauss reconstruction. Okay. So, in the green Gauss we will be using a form of the Gauss divergence equation, which is called the Green's theorem. Okay. If you have taken a math course, you might be knowing about it. Okay. So, what it does is that if you want to get a gradient, okay, you can in a given volume, okay, you can use the information at the interface. Okay. So, for example, these are my faces. So, you can use the information information at the interfaces to calculate the volume at I here. Okay. So, the formulation is like this. So, if you have del phi d omega, whereas the d omega is basically the, you can take elemental volume here for all the volume is basically take all the faces and then you get the value at the or at those faces, okay, and then you integrate it. Okay. Basically, if you have let us say 4 faces in your cell, okay, then you will have all 4 that will be integrated. Okay. So, this there will be a summation sign here. So, this we are doing, this is the phi on face, okay, we can call it phi f maybe, and this is your delta phi at I. Okay. So, you can, if you know the variation of phi on the face, okay, on each of these faces. So, you basically integrate it along each face, add it and keep on adding for all the faces, and these sigma that you see here, okay, that is the gamma that you see here, that is nothing but the area of that interface. Okay. So, if you assume that the variation on the face is basically linear, right, this is phi f, right. So, if you assume that, then let us say this is the variation along the face, right. No, I should plot it at the center, just one second. Okay, let us say this is the variation along the face, okay, and the things are varying normally. Okay. So, if you want to calculate the term which is phi f d sigma, okay, okay. So, this is your variation, okay, and this is the center of the face, okay, I call it f, okay. This is my center of the face. So, what you can do, if you want to calculate this phi f or the phi variation, okay, not phi f, phi along this, okay, this is my variation of phi, and I want to calculate it along the entire face. So, this will be my area, right, Z1. Okay. So, what you can do, because the variation is linear, you can take the value at the center which is my phi f. Okay. I should not call it phi f here, this is okay. So, my phi df, the integral value of this will just become phi f into the area which is this one, basically delta gamma, right. So, what I am trying to do is that the area under this curve, because of the linear variation, is equal to area which is just you take this region. Okay. So, if the variation is linear, the integral quantity can be written as the value at the face center multiplied by the size of the face, okay, the length of the face. Okay. So, this is what I have done here. Similarly, because the cell variation is also linear, the variables are varying linearly in the cell also. So, this can also be written as delta phi I omega I, right. So, if you do both of these here, assuming the linear variations, will become delta phi I omega I will become sigma phi f, and let us call it delta S f, and because this is along the normal. So, you have to basically use this quantity which is n k, the face normal. Okay. Remember, this is a gradient quantity. So, this is a vector, okay, and the right hand should also be a vector. So, there will be a normal to the face n k, right. So, you can rearrange it and finally, you will have this formulation. So, you are getting the gradient by just knowing the face, the value at the face center. Okay. Remember, this k should be k value should be at the face center. Okay. Then only you can basically convert this integral sign into the summation sign, okay, as we saw the example here. Okay. So, the phi k is the value at the face center. Now, the question I have is, how do you get value at the face center? Okay. So, that is the question we have. Okay. So, it is important to get the value at the face center if you want to calculate the gradients at the cell center, right, in the Green-Gauss procedure. So, what we will do, there are two approaches, basically one is cell based, and in fact, this information that you will get in Fluent also, that which kind of Green-Gauss that you want to use, or in open form also. Okay. So, we will what we will do in the next class, we will look at how to get the value at the face center, and then what we will also see that how to calculate the gradient at the face also, because as we saw that the viscous flux requires the gradient at the face. Okay. So, we will look at both these aspects in the next class. Thank you very much.